251ers, remember the short video last time? You really liked that. I think this one's going to be short too. We'll see how it goes. So in this video, I learned you, I guess in the last video, I learned you a little bit about what a gyre is, what a surface current, the different types of surface currents, and about the equatorial countercurrent. I showed you where some of them are. We can go into a little bit more detail about some of the generalized subtropical gyres. I'm going to put my keys over here so they don't click while I'm walking around. So in general, subtropical gyres are bounded by the equatorial current on one side. Depends on if they're in the north or southern hemisphere, which side these things all are. But they're bounded by an equatorial current, the western boundary current, a northern or southern boundary current, and an eastern boundary current. And you're like, Professor Sylvan, are you serious about that? Of course, they're bounded by the currents that are the four sides of the pointy compass thing, right? What else would they be bounded by? All right, touche, whatever. So basically, they're bounded by currents that have directions attached to them. Remember, equatorial current is the other one. If it's a northern subtropical gyre, then the equatorial countercurrent is going to be on the south end of that gyre, and the reverse is true for the southern ones. So subtropical gyres in the northern hemisphere, they move clockwise, and in the southern hemisphere, they move counterclockwise. So in the northern hemisphere, they're going like this, and then in the southern hemisphere, they're going like that. Right? And this is because Coriolis pushes wind and subsequently water in different directions in the northern versus the southern hemisphere. So, and the reason that subtropical gyres are really important in oceanography, besides for the fact that they move around a lot of water, and therefore a lot of chemistry, they're the deserts of the ocean. So did you know blue is the desert color of the ocean? When you see beautiful, beautiful blue water, that's because there's not much living in it. And there's also not much particles, which might have nutrients, which allow things to live in it. Blue is like the color of not much going on in the ocean. It's still beautiful, but it's kind of the desert color of the ocean. Excuse me. I mentioned there were 5 subtropical gyres, right? North Pacific subtropical gyre, South Pacific subtropical gyres, fun tongue twister. North Atlantic subtropical gyre, South Atlantic subtropical gyre. Oh, where is the North Indian subtropical gyre? It's what we call India and part of China. Well, I guess maybe part of Pakistan. No, is that right? No, Pakistan's over there, part of China. Indian Ocean is mostly in the southern hemisphere, so there's only an Indian subtropical gyre. We don't have to put any direction in front of it since there's only one. But more importantly, so that's where they are. I had pointed them out on one of the earlier slides. Again, centered around 30 degrees latitude. The colors that you're seeing here are chlorophyll A concentration. This is something called the CWIFS satellite, is what's generating this data. So it's the global biosphere. CWIFS was a satellite that went up and measured chlorophyll from space. So, and if you remember, we've talked about the fact that, you know, the gold seal is always measuring something that you actually have your hands on, but you could only do that with so many things, the gold standard, I should say. So satellites are great for measuring things on a global scale, right? No way we could do that with hand samples globally. And so CWIFS was a satellite that went up to measure chlorophyll, so it tells us basically how much biomass, how much plant biomass there is in the world. And these blue colors, the more blue it is, down to purple, the less chlorophyll there is. And you can see the place in the world where there is the least amount of surface chlorophyll. Chlorophyll is always going to be on the surface because chlorophyll indicates plants, and plants need light, so they're not going to be very far down into the water, right? The least biomass out there is the South Pacific subtropical gyre, and there's also not very much in the South Atlantic subtropical gyre. They're very far away from deserts, it turns out. Anyway, these are where the 5 subtropical gyres are. And you can see, don't take my word for it, this is proving to you that these are the deserts of the ocean. Okay. Okay. Don't let me ramble, 251ers. George is supposed to stop me from rambling, but he doesn't always do a good job. Yeah, I'm looking at you, George. Okay, so western boundary currents occur when equatorial currents meet the land on the western side of an ocean basin. Something to keep in mind and wrap around your cute little 251 heads is that the western boundary current is always on the eastern side of a continent. So don't let that confuse you, because it's the ocean that the current is named after. So the western boundary currents, here's one here. This one happens to be called the Gulf Stream. We know a little bit about that one. And then here, I forget what that one's called, but it's also on the eastern side of South America, but it's the western boundary of this subtropical gyre. The Coriolis effect deflects currents away from the equator. So if you remember, the way these are formed, we have the trade winds blowing this way north and south of the equator. We've talked about the kind of equatorial countercurrents, and we'll get back to that in the upcoming slides. But just north of that, the trade winds are blowing water. They're blowing it this way, right, on both sides of the equator. In the northern hemisphere, that water is going to be pushed off to the right because of Coriolis. And that, when it gets pushed off to the right and moves up, just like we talked about the paths of hurricanes, so also goes these major current systems. Hurricanes start more down here, but these are starting up here. So this is coming up and forming the eastern boundary current. The western boundary current. And the same thing here, except in the southern hemisphere, Coriolis is going to push down to the left. Right? So therefore, western boundary currents, because they're going either north or south from the equator, equator is where warm water is, they're carrying warm water from the equator to higher latitudes, right? And so that's why it's great going up in New York, being on the East Coast, where warm water was just brought to me. I want the warm water, I would say. Gulf Stream, bring it to me. And it would happen. Boom. On the West Coast, not the case. You get the cold water coming up from Canada. Like I said, these form the western boundaries of subtropical gyres. By the way, this is just showing us the ones in the Atlantic Ocean. The ones in the Pacific and the Indian, if this map was to continue all the way in both directions, those also have the same rules. So eastern boundary currents are turned by the Coriolis effect and land barriers towards the equator, right? So these are coming from the prevailing westerlies. Westerlies are pushing water that way, in the higher, the 40s, 50s, that kind of latitude. And then in the northern hemisphere, water moving to the east is going to be pushed to the right. If you're moving to the east that way in the northern hemisphere, you're going to be pushed that way, which is south. And so this forms the eastern boundary currents. If you're in the southern hemisphere, you're still pushing water that way, and then it's going to be pushed off to the left, which is north in this case. So these occur on the eastern boundary of ocean basins, which again, don't let your pretty little 251 minds get confused. This is the western side of the continents, right? So it's always kind of opposite, right? Because I'm getting at. Okay. The eastern boundary currents are basically the opposite of the western boundary currents. So the eastern boundary currents, they are carrying cool water from high latitudes towards the equator. So in the northern hemisphere, the western boundary current on the other side of North America is what's bringing the cold water down to Southern California and the whole rest of the West Coast. But if I go swimming off of Seattle, I might not be surprised that the water is cold. It's more that when you go swimming off the coast of Southern California, you're like, what the what? It's so cold. They form the eastern boundaries of subtropical gyres. Those are eastern boundary currents. Okay. Whew, we are making it through this, 251ers. We should talk about the shirt real fast. This is a band called Wrong Day to Quit. And they had a woman who sang with a very pretty voice, and also yelled with a really awesome voice. And if any of you, I don't know that this is why they named the band that, but if any of you are fans of the 1980 movie Airplane, as I am, because I'm super sure and I like that kind of stuff, I always think about Leslie Nielsen. He was in it. Not Beau Bridges, but their father, the Bridges, the elder Bridges. I forget his name, but he was such a sweet guy. He was always saying, "Oh, I guess I picked the wrong day to quit sniffing glue," right? Because they were having trouble landing the airplane, and it got progressively worse as the movie went on. Wrong day to quit. Come on, it's a good name. Okay. The equatorial countercurrents move a really large volume of water westward due to the north and south equatorial currents. I'm sorry, I got that backwards. That's why there was a pause. I confused myself. This is setting up the whole situation. Okay, so we're going to start from the other way. And I'm actually, so north, south, west, east. Okay, I'm going to act this out for you. First, I'm going to check and see who just texted me, because I'm a really good teacher. And I don't know, maybe that's important. Who is it? Okay. So we know that this is trade winds. Trade winds are pushing water to the west. In the northern hemisphere, this will eventually curl up to the north, but they push water to the west along the equator, just north and south of the equator. So a large volume of water moves westward due to the north and south equatorial currents. This water piles up on the western margin of ocean basins and is not turned by the Coriolis effect because that's very small at the equator. So if you are looking at sea surface height across the Pacific Ocean, if this is South America over here, and this is like, you know, the Western Pacific Islands over here, like Indonesia and the Philippines, sea surface height is going to be greatly exaggerated, but it's actually kind of like that. It's much higher on the western side than it is on the eastern side because all of this water is pushed in that direction and it kind of piles up. And then because there's no Coriolis effect at the equator, it doesn't get pushed off in one direction or the other. The stuff further north does, and that's what forms the bottom of the subtropical gyres, but the stuff closer to the equator on the southern end of these waters, these currents being pushed that way, it does not. Therefore, don't take my word for it. This is true. You look it up. Average sea level is up to 2 meters higher on the western side of ocean basins than on the eastern side. That's like me-sized, slightly taller, or slightly less. You don't know how tall I am. I'm really tall. 2 meters is about up to here on me. But that's a lot of water. 2 meters higher one side or the other. Gravity, and there's no Coriolis to push it in one direction or the other, so gravity is going to be like, all right, enough of this. We got to go the other way. So the water flows east. East is now this way, so this water was really high, but then the water is going to start flowing back that way. Under the influence of gravity, creating a narrow current that flows between and in the opposite direction of the north and south equatorial currents. This is called the equatorial countercurrent. So the equatorial currents are the ones that are going in the direction of the trade winds, north and south of the equator. And then basically the equatorial countercurrent is what goes in between those. This is the most pronounced in the Pacific because the arrangement of the land on the western side of the Pacific traps the water and the large size of the equatorial zone in the Pacific. For 2 reasons. Really? Okay, that's next. I'm going to take a step back so I can actually show you, get back to it, show you kind of what it looks like. We're going to have to go back to the last lecture. But I want this to make sense because this is important, and this also becomes really important for us understanding El Nino. So sorry that there's like a lot of clicking forward and backwards in these lectures, but hopefully will help things make more sense. So the trade winds are blowing this way, okay? And It's okay that this is actually slightly offset from the equator, but trade winds are blowing to the west. And so what you see here is the southern equatorial current and the northern equatorial current. And they're pushing that way, right? Water piles up over here. It has nowhere to go because Coriolis won't let it, and so it literally sneaks back in between, just in between, a thin band in between these equatorial currents, and that is called the equatorial countercurrent because it's going against the grain, just like minor threat. Or are they out of step? They're out of step. Does that make sense? Hopefully that makes sense. So, and it mentioned that this is actually most pronounced in the Pacific Ocean. Again, this is similar to why, unfortunately, they get worse hurricanes over here, or tropical storms, I should say. It's because the Pacific Ocean is a lot wider, so that those winds blowing across the entire ocean, they get a lot of what we call fetch. And so there's a lot more fetch because it's a much bigger ocean, so they can push a lot more water onto this side. And then there's also this kind of land trap where the water can't actually go any further, so it just kind of piles up, and then it goes that way. This going this way part, that's normal, and happening kind of all the time. El Nino, we can learn about this. El Nino is also normal, by the way. I'm sorry, I don't mean to say that. El Nino is also normal. It's a pain in the butt, but it's normal. But one of the things that initiates El Nino is that the trade winds kind of die down. And so this movement of water back this way becomes a much larger phenomenon. Okay. Wow. We did it. We did it. We went through all of these things. This really probably could have been one chapter, but it's okay to have bite-sized pieces. So now you know about subtropical gyres. You know that eastern and western boundary currents bound those on the two different sides, resultant from winds and Coriolis. You know about equatorial countercurrents, and when we go on, somebody closing their door very loudly out there in the basement of wherever it is that I'm teaching this. When we come back, we're going to talk about Ekman. He's a smart guy, figured out this spiral thing. And this has big implications on currents on small scale and, well, mostly small scale, but also some implications for larger scale currents related to coastal areas, also related to the equatorial countercurrent. So important stuff. That's what's going to happen next. And I hope that you're enjoying this, learning something about currents, enjoying the background color, and George is telling me, it's like, yeah, enough of that. I'll see you in the next video, 251ers. Until then, please, just be nice to each other, be good people, and see you later.
Looks like I picked the wrong week to quit sniffing glue.